Hey, welcome back. So now we're in 6.5, the last section I want to cover in the differential equations chapter. We're looking at a certain class of differential equations, the first order linear differential equations. So they're first order because there's a first derivative in there floating about, and that's the highest derivative. And then linear, I believe it means that the y component is not squared or cubed, or you don't have like the sign of y prime or anything like that. They give you a standard form in the book again, which may or may not be similar to what you'll see when you take your sort of standard differential equations class, but it's probably close. So anyways, standard form, it looks like this. So you have your y prime part, and then you have some function of x times y, and the other side you have some other function of x. Okay? We're going to give you a method for solving this by hand using what's called the integrating factor. Okay, so solving, you use the integrating factor, which is kind of a clever method for doing this. So in the book they give you an answer that you could always use, but I need you to do the process. That's really the important part, just learning sort of the algorithm that you have to follow in order to do this. A lot of math seems, especially with the computation, is just memorizing algorithms at this point, which, you know, the truth is you could probably program the computer to do all of this, and we're kind of not exactly as good as computers, so why do we bother? You know, that's a big question. So anyways, we need to know how to do at least the basics and kind of, okay, so let's look at an example just to see how this goes. So I have y prime plus y equals e to the x, and I want to find, you know, the solution is some function y that satisfies this equation. So I need to first make sure it's in my form above, so you know the form dy over dx plus something times y. In this case, the p of x is 1, and then the q of x is e to the x. So p of x, maybe I'll just make the thing in front of y is just 1, and the other side, q of x is e to the x. Okay, so it's already in the form. If it's not in the form, you're going to have to change it. Okay, and you definitely don't want a coefficient on the y prime part there, so you can't have anything in front of that. Okay, once you verify it's in the form, you construct your integrating factor mu, that is the Greek letter mu, and it's e to the integral of px dx. So in our case, it's just 1 dx. And you can integrate 1. The integral of 1 is x. You don't need the plus c. Okay, that's not going to help things. It's just going to kind of confuse things. And sometimes you have to be a little careful with the mu, depending on sort of where you're solving your differential equation. But you'll see that once you get into the actual class later in your degree. Okay, so anyways, for now, let's just multiply. We take this and we multiply the original equation by it. And that's where the magic happens. So I multiply everything by e to the x. E to the x times e to the x, what is that? You just add the exponent, so you get x plus x, which is e to the 2x. Okay, so e to the 2x. So on the left-hand side, by doing this, what you've created is the result of a product rule. Okay? It's the derivative with respect to x of e to the x times y. Okay? And you could verify that this is the case. So let's come over here and verify that. If you leave e to the x alone and take the derivative of y is 1 times y prime. So it'll be y prime. And then plus the derivative of e to the x is e to the x, and then you leave y alone. And so, yeah, sure, we got it, right? I mean, this method is done because of that. It allows us to take the left-hand side and collapse it in a way that allows us to integrate both sides, and then we'll have our solution. Okay, so once we collapse it into the derivative of e to the x times y, I can then integrate both sides with respect to x. And then on the left, the integral and the derivative kind of cancel each other out, and you're just left with e to the x y. And on the right, you're going to have to do a u sub for 2x. So there's going to be a constant of 1/2 floating about. Right. So this will be integral of e to the u times du over 2. You can factor out the 1/2, integral of e to the u du. And you end up with 1/2 e to the u, which back subbing will give you 2x plus c. And then if you want the explicit solution, you could divide everything by e to the x. So you'll get y equals 1/2 e to the 2x over e to the x plus c over e to the x. And clean it up a little bit. So if you have a quotient, a to the x over a to the y, that's equal to a to the x minus y. So in our case, e to the 2x over e to the x is e to the 2x minus x, which is just going to be e to the x. And then plus, we could rewrite c over e to the x, c e to the negative x. In this case, the constant c will not absorb that e to the negative x. Okay, that would change the picture significantly. If you just have 1/2 e to the x plus c e to the negative x versus 1/2 e to the x plus c. Those are different graphs altogether, and I hope you can appreciate that. If not, go on Desmos and kind of take a look at the differences. Right, so that's our answer. Here it is. And you can hand that off to whoever wants it. Let's look at another. Okay. So the magic of the integrating factor, so the magic of the integrating factor is that once you multiply through your original form by mu, so you'd have mu y prime plus mu times p of x y equals mu times q of x, you can collapse that left-hand side, and it will always work, into the derivative with respect to x of mu times y. Okay? And then you can take the integral on both sides and you're done. Okay, so that's the magic. Okay, so again, let's look at another problem, another example. Let's try x times y prime minus 2y equals x squared. And well, let's go ahead and make this one the quiz question for the day. Let me mark it down in my notes so I remember. Notes. Wherever you are. There we go. So 6.5. You have to do xy prime minus 2y equals x squared. Okay. Right. So first off, notice it's not in our standard form. We need to have y prime by itself in order to proceed by multiplying by the integrating factor. Okay. Okay, so what we need to do then is divide everything by x. So we get y prime minus 2 over xy equals x squared over x is just x. So our mu then, our p of x is negative 2 over x. So mu is going to be e to the integral of negative 2 over x dx. We can integrate that, e to the negative 2 times the integral of 1 over x dx. That's a natural log. I have e to the negative 2 ln. We're not going to worry about the absolute value. That could be an issue if you're later on, but right now we're just going to kind of forget about that and forget about the plus c. Okay? So e to the negative 2 ln x. We could simplify this, but not as it sits. In order to simplify it, we need kind of the ln and the e touching each other. So we have to first bring the negative 2 inside the natural log using the power rule. So I'll have e to the ln of x to the negative 2, and then you can simplify. But you can only do it once you have the e and the ln's kind of touching, right? Okay, so mu will end up being just x to the negative 2, or 1 over x squared if you would rather. Okay. Then we can multiply our first order linear differential equation, and we get y prime over x squared minus 2 over x cubed times y equals 1. X over x squared is 1 over x. You could always just go directly to collapsing it. So it's always going to collapse into mu times y. So mu is 1 over x squared and then times y. On the other side I have 1 over x. Integrate both sides. Integral with respect to x. On the left, the integral and the derivative cancel. We have 1 over x squared times y. On the right, that's a natural log, absolute value of x plus c. And then finally, if you want an explicit, you can multiply everything by x squared. You end up with x squared ln absolute value of x plus c times x squared. And again, this constant won't absorb the x squared. You'll get a different picture, okay, if you did that. Right. So one picture, the equation is just going to be shifted up and down by c if you get rid of the x squared. But it's going to have a weird effect if you're adding in an x squared to that original function. It's going to make it look different as you change the c values. Okay? So again, you might want to go to Desmos and take a look at that if you're interested. Okay. Okay, let's move on to these mixing problems that you'll probably see again later, maybe. In particular, there's, okay, so in this example, we want to show that this differential equation models the mixing problem. And I'll explain what that is here after I write out the formula. Plus R2Q over sub 0 plus R1 minus R2 times T equals Q1 R1. Show the following differential equation models the mixing problem. Okay, so what is the mixing problem then? You have a tank of fluid, some solution, they'll call it, and then you have a concentrate on top of it. And the Q is how much of the concentrate is in the solution. So you'll have a tank filled with to some level with something. Usually I think in terms of salt water, okay? And there's an input and kind of an output. So there is the spout, which is going out, okay? And then there's another kind of input spout to go in to the vat. Okay, they'll give you an initial amount of solution that'll be V sub 0. And the units are kind of important. You want to look at those gallons of solution at time 0. They'll give you an initial amount of the concentrate in there. So if we're talking salt water, the initial amount of salt water would be Q sub 0. Or pounds. This will be in pounds, so pounds of salt in the salt water. Yeah, so let's just call everything salt water. Okay. Salt water. And it could be, you know, that it's just distilled water at first with no salt in it. Okay. So Q sub 0 is the number of pounds of, so the Q sub 0 can be 0. Okay, pounds of salt in the salt water at time t equals 0. Big Q that you see in the differential equation is the amount of salt in the solution at any given time t. Okay, and that's kind of what we're after. We want a formula for predicting the amount of salt in the tank. Okay, and you assume the tank is well stirred, so like the salt isn't going to bunch up on the bottom and never leave the tank or anything crazy. What else? There's going to be a rate in of solution that'll be R1. So this is there's R1 gallons per time unit. In this case, we'll say gallons of solution per minute going into the tank. And the number of pounds of concentrate is a constant. So Q1 pounds of concentrate per gallon, or in our case, salt. And then they'll tell us on the output there are R2, how much is going out of it, right? So R2 gallons of salt water. So I need to replace this word solution with salt water. So R2 gallons of salt water per minute leaving the tank. Okay, so somehow we want to show that this differential equation back here, and maybe I should zoom out a little bit so we can see what's going on. I want to show that differential equation up there is a model for the tank problem. And there, you could do this on steroids, so you could have like 10 different tanks, you know, where there's stuff going in and out of them, and you want to know how much salt ends up in tank 5 and things like that. So it's kind of a neat thing to work with. So we just want to show that this differential equation works for this problem, and the way to do it is to basically just say, okay, the rate of change of the solution with respect to time is going to just be the difference between the amount of salt going in and the amount of salt going out. Simple, right? Okay. So maybe I should put salt rate in and salt rate out. One thing to note then about these two rates are the units, and that's going to be, at least in my opinion, the key to determining kind of the formulas for these two terms. So the salt rate in, think about the units. It has to be in pounds per minute, right? And then the salt rate out, also pounds per minute. So in particular, for salt rate in, you can produce a factor of pounds per minute by just multiplying R1 times Q1, right? Because R1 is going to be gallons per minute. R1's gallon per minute. And Q1 is what? Pounds per gallon, right? And you notice if you do multiply those out, clearly the gallons are going to cancel, and you're left with this R1 Q1, 1 pounds per minute, which I decided to write as BLS for some reason. And you could see that factor, that term, overusing the word factor, that term is in our differential equation right here. Okay, so it seems like we're on the right track. The other formula then for salt out is a little more complicated, because they only give us the one factor, and then the Q factor, the Q2 we're looking for is variable. So it's dependent on the amount going in and then the amount going out. So in particular, then we're going to have the R2 factor, which is in gallons per minute. So R2 gallons per minute, and then we're multiplying by something that's in pounds per gallon. Okay, so the pounds part is kind of easy. That's just the Q, right? And we know at any given times t, there are Q of t pounds of solution in the tank. If you look back over at the little tank picture, I just boxed it in red. Then that is over the number of gallons that are currently in the tank. So to figure that out, you kind of do a little linear equation, right? So you're going to start out with V sub 0 gallons, but then over time it changes because there's stuff coming in and there's stuff going out. And really the amount of change is the difference between those two, right? So after like 1 minute, there's going to be R1 gallons going in and R2 gallons going out. So after 1 minute, there's R1 minus R2 times 1, which in general will just be T, additional gallons going in or going out. Okay, so you just go the original amount plus this difference between, so for example, if there's 5 gallons going in and then 6 gallons going out, so I'm writing over here to the left of this on the screen here. So if there's 5 gallons going in to the tank, and then there's 6 gallons going out, and you start with 100 gallons, after 1 minute, there's going to be, well, let's say there's 4 gallons coming out, right? After 1 minute, there's going to be an extra gallon coming in because it's just 5 minus 4, right, times T. That would be our formula in that case. So after 1 minute, there's 1 extra gallon because there's 5 gallons coming in and 4 gallons going out. Okay, hopefully that's kind of clear. Okay, so that ends up being the formula, and you notice, if you multiply that all out, what do you get? Well, you get this other factor, or this other term rather. Use the word factor when you're talking about multiplying two products together. Use term when you're talking about things being added together. Okay, so that's sitting right there, and then it's kind of clear, at least from this picture, I think that this thing is actually the model for the mixing problem. Okay, so in general, they'll have you go through this with particular values, and you have to, of course, solve for your. So let's look at one of those on WebAssign. Let's go on the WebAssign here and see what they got. And where are you, WebAssign? So let's go on to 6.5. I want to make sure I got this equation sitting here on my lap. And scroll down, probably one of the last ones. Okay, let's try. Dare we try the last one? The last one looks like it's kind of just in general. This one looks like it's just not even that kind of problem. Okay, let's try this guy and see how it goes. So we have a 500-gallon tank. It's full of solution containing 50 pounds of concentrate. So it's full. So V sub 0. So we're identifying all these V sub 0, Q sub 0, R1, R2, all that junk. Okay, so in this case, if we draw out the picture again, okay. Okay, so the initial amount, it's 500 gallons and it's full. So V sub 0 is 500 gallons. The initial amount of concentrate is Q sub 0, so that's 50 pounds in this case. Starting at time t equals 0, distilled water is administered to the tank. So distilled water basically means that your Q sub 0 or your Q sub 1 is 0. Okay, 0 pounds. I keep wanting to put BS, LBS per gallon. And then it's saying that we have the concentrate is coming in at 10 gallons per minute. So R1 is 10 gallons per minute. And then it's withdrawn at the same rate. Okay, so it's coming out also at 10 gallons per minute. And we need to find a function for it, okay? And then probably answer some questions. So here we go. Salt in is going to be basically 10 times 0, which is just 0. Salt out is going to be Q times R, which in this case is 10, all over V sub 0, which is 500, plus R1 minus R2, which are just both 10 times T. So that'll be 10Q all over 500, in other words, Q all over 50. And so our differential equation, dq over dt, is just going to be salt in, which is 0, minus salt out, which is Q over 50. And then we just solve that differential equation to get our formula. So I have dq over dt equals negative Q over 50. And integrate both sides. Excuse me. So I have Q. Whoops, I didn't separate. Sorry. So dq over dt equals Q over 50, negative. Separate, so dq over Q equals negative 1 over 50 dt. Integrate, and I get Q, ln of absolute value of Q equals negative 1/50th T plus C. And then solve that, you end up with a Q equals E times, so I'm exponentiating e to the negative 1/50th T times e to the C eventually. And so Q will equal C e to the negative 1/50th T. And they tell us the initial amount of concentrate is 50. So 50 equals C e to the negative 150 times 0. So C is equal to 50. And that gives us our model. So Q is equal to 50 e to the negative 1/50th T. Okay. So let's go back and see if that's what the answer is. Yep. Find the time at which the amount of concentrate in the tank reaches 15 pounds. The amount as time t goes to infinity is pretty easy. Let's do, I guess, one thing at a time. Okay, so find the amount find the amount of concentrate when the tank reaches in the tank. Find the time. Oh, find the time. Okay. And how many pounds? Sorry, 15 pounds. Okay, so you just set Q equal to 15 and solve for T. So this is part A, this is part B. So So 15 over 50 is 3 over 10. ln on both sides. Negative 1/50th t equals ln of 3/10. Then multiply both sides by negative 50. And you get an approximation for that. 50 times 50 times ln of 3 over 10. And I'm getting about 41.53 minutes or seconds or something. Is that the problem? Yeah. I did something wrong. I got 60. Oh, it's no, that's not it. Oh, it's 5s. No, 3. What did I do wrong? Oh, I just put it in my calculator wrong. That's all I did. Crud. All right, hold on. 68.2, right? Yeah, and that should be right then. Yeah, 60.2. Find the amount of concentrate as t goes to infinity. So that's just a limit problem, taking t to infinity of 50 e to the negative 1/50th t. So you could rewrite that as the limit as t goes to infinity. 50 all over e to the positive 1/50th t. And then if you put in t values like 50, 500, 5,000, that denominator is going to go to infinity. And that type is always 0. Okay, so over time, there's not going to be any salt in the water if you had an infinite amount of time, I guess. Okay. So I don't know. Let's look at this other one, I guess. What the heck is this guy? Of course, you don't have to watch. You can always just stop the video and do it yourself if you need help. Okay, so this time we have a 232-gallon tank full of distilled water. So V sub 0 is 232 gallons, and Q sub 0 again is just 0. Coming in, we have 0.5 pounds of concentrate per gallon. 0.5 pounds. So this is Q1 per gallon. And then the rate enters at a rate of 7 gallons per minute. So R1 is 7 gallons per minute. And then it's well stirred and withdrawn at 5 gallons per minute. Okay, so it's coming out at 5 gallons. So that would be R2, 5 gallons per minute. And then your rate in, of course, is going to be 0.5 times 7, so 3.5. Your rate out is going to be big Q times 5 all over V sub 0, which is 232, plus the difference of R1 and R2, that's 7 minus 5 is 2T. That's 232. At what time will the tank be full? Right now it's half full. It says in the problem, right now it's currently half full. So it's 232 gallons. So you don't really need calculus to figure this out. Divided by 2, 1, 1, 6. So we need to get 116 more gallons in there. And because of the difference between the rates being 2 gallons, it basically you just divide that by 2 and that'll give you your answer. 6 of 58. So part A, how long till the tank is full? And again, it's just because you know it's initially half full. You know there's 230 gallons in the tank, so therefore there's currently 116 gallons in the tank and you need 116 gallons more. And then you're saying that every minute there's 2 additional gallons coming in because of the difference between the rate going in and the rate going out is 2. 7 minus 5 is 2. So it's going to take 116 divided by 2 minutes, in other words, 58 minutes. Okay. So no calculus there. At what time? At the time the tank is full, how many pounds of concentrate will it contain? In order to pull that off, I'm going to need the formula for Q. Okay, so part B, I'm going to have to work with my differential equation and solve it, right? So, and okay. Anyways, there's a bit of a mistake right here. The initial V sub 0 is 116, not 232, because it's half full, so it's 116 here. Okay. So part A, they want, what do they want? We got part A. How long until part B? At what time? At the time the tank is full, how much salt is in there, or how much concentrate? So when tank is full, how much concentrate is in the tank? So we need a formula for Q, in other words. So we're going to have to begin with the differential equation dq all over dt, and that will equal rate in, which is 3.5, minus rate out, which is 5q all over 116 plus 2t. And this is, it may not look, it's not separable. It's first order linear differential equation, so I could add this 5q thingamajig to the other side, and that'll equal 3.5. And then I could get my integrating factor. Mu is e to the integral of 5 all over 116 plus 2t dt. You factor out the 5, there'll be an extra factor of 1/2 from the u sub, and at the end of the day it'll be ln of the absolute value 116 plus 2t. Then you could use a power rule to bring this up and in, and you get e to the ln of 116 plus 2t to the 5/2. Assuming time is positive, you don't have to worry about the absolute values. The e and the ln will cancel, and you're just left with 116 plus 2t to the 5/2. Then you multiply through, and you collapse the left-hand side into just mu, which in this case is 116 plus 2t to the 5/2 times q. On the other side, we have 3.5 times mu, 116 plus 2t to the 5/2. And then we can integrate both sides. So I'll have on the left 6 plus 2t to the 5/2 times q. On the right, I have 3.5 is the same as 7/2. There'll be a 1/2 from the u sub, so it'll be 7/2 times 1/2, and then from the power rule, 6 plus 2t, 5/2 plus 2/2 is 7/2, multiplied by the reciprocal of 7/2 is 2/7. And then we can clean it up a little bit. this will equal, well, these cancel, and you're just left with 116 plus 2t, and we need a plus c in there. 6 plus 2t to the 7 halves divided by 2 plus c. Then you could divide both sides by 116 plus 2t to the 5 halves. You get q equals, subtracting exponents for the first factor, 116 plus 2t to the 2 halves, all over 2 plus c all over 116 plus 2t to the 5 halves. Then we have to figure out what c is, so you use your initial amount of concentrate, which is 0. So you're plugging in 0 for t and 0 for q. So that'd be 116 all over 2, I guess, plus c all over 116 to the 5 halves. Then solve for c. So we get c over 116 to the 5 halves equals negative 116 over 2. Multiplying both sides by 116 to the 5 halves, adding exponents, so 116 to the 5 halves times 116 to the 2 halves is 116 to the 7 halves over 2. Then we could rewrite our equation. Let me zoom out a little to make that possible. And we're looking at q equaling 116 plus 2t over 2 minus 116 to the 7 halves all over 2 times 116 plus 2t to the 5 halves. And then we want to know how much concentrate is in there after 58 minutes. So you just plug in 58 wherever you see a t, and hopefully that'll be the solution. Let me put that in my calculator. And I'm getting 105.747, 105.75 pounds if you go the 2 decimals, which is the answer. Okay, at the time the tank is full, how many pounds of concentrate will it contain? So they changed the question on you. You guys can handle that. So part B, instead of solution entering with instead of it being 0.5 pounds, assume it's 1 pound and basically go through the whole problem all over again, just changing that factoid. Okay, so I'm going to leave that to you and get the heck out of here, and hopefully you can do the rest. Okay, so thanks for watching, and we'll see you next time.